Hey there. So, in this lesson, we'll be talking about optimized perimeter and area. So, I saved this lesson for last because it's a bit difficult to understand, and I'm probably not going to test on this because it might be a little too much, but I'm going to teach it though. So, let's talk about it. So, optimization. So, what is the optimized area and perimeter? Well, in terms of, okay, I want you guys, okay, let's read the definition first and then I'm going to give you an example. So, optimized shapes often have the largest area relative to the smallest perimeter or surface area. So, it's the amount, the largest amount of stuff you can put in with the smallest amount of packaging in that sense. An optimized shape often resembles a square or a sphere. Now, you're not going to get this in the textbook, but I'm telling you right now, it often resembles to a sphere or a square, or the closest thing you can get to it. They're often, you can actually figure out what the optimized shape is using a plot on a graph when the curve is at either its highest or lowest. When you're plotting a graph, and you see either the top of the curve or the bottom of the curve will be your optimized shape. You can also use calculus, but that's beyond this course. So this is probably the best way for you guys to sort of see the optimization. You'll see in a couple seconds. And you may have to use substitution techniques. In this lesson, you have to use substitution techniques. I'm not quite, in the homework you may not, but all you have to really know is anything that resembles like more of a sphere or a square is most likely the most optimized shape. And I want you guys to think of an example. Think of a water balloon. So a water balloon is basically a piece of plastic and you can fill water and it sort of blows up, right? Well, the balloon always wants to have, it doesn't want to stretch, right? So it wants to have the least amount of surface area as possible, the smallest surface, because the balloon does not want to stretch. Basically, that's what a balloon is. It's made out of plastic, so it wants to retain its shape, but it's going to fill up. So it's going to try to fill up as much water as possible with the least amount of surface area. And if you look at the shape of a balloon, when it blows up, it's more of like a sphere or a circle, a sphere or like a ball. It's not a square, it's not a rectangle, it's not any other weird shape. It's always a sphere. And you can tell right away that that is the best shape possible to fit as much water as possible with the least amount of plastic stretched. Okay, so you have that example. Let's get into some examples to sort of understand what's going on. So, Latoya wants our new vegetable garden to have a top area of 60 meters squared. So we have area is already given to us. Let me just get my comment tool here, my pen. So area is already given to us. We know what the area is going to be. So you want to have an area of 60 meters squared. The garden will be a rectangular and surrounded by a fence. What dimensions will require the least amount of fencing to its nearest degree meter? So we already know it's going to be, we already know the answer. It's going to be a squared because most optimized shapes are a square or a circle. And because we're constrained, we know it's going to be rectangular, so we know it's going to be a perfect square. But it's gonna automatically seem that you do not know that. So we're gonna do this the long way around to show you that it is a square. But the answer is a square. So you know it's a square. So anyways, so the equation for the area is length times width, right? And if you isolate for, basically to do this problem, you need two equations. And the two equations that are given to us is the area equation, that one equation that's given to us, and also another equation is given to us is the perimeter equation, and it's just basically adding up all the sides. So we're gonna substitute one equation to the other, and more specifically, we're gonna substitute the area equation into the perimeter equation. So we're gonna isolate for W. So what I'm gonna do here is gonna multiply both sides by L, and multiply this side by L, or more specifically L over 1, the same thing. And this L, oh wait, you don't multiply, you divide both sides. Sorry, my mistake. Let me just erase that. So you're going to divide both sides by 1 over L, divide this side by 1 over L. That's the same thing as dividing. If you do that, maybe it's easier for me to show it to you this way. Divide both sides by L, divide both sides by L. This L cancels out with this L, and you end up with A over L equals W. Okay, and in a sense, we know what A is. A is 60 degrees over L, 60, basically 60 meters squared equals W. So W equals that. So W equals 60, whoops, 60 over L. Okay, so what is the perimeter? So we're going to substitute this equation into the perimeter equation for a square. So basically we have ourselves a square here. So you're adding all the sides up in short. That's what you're doing. So this is the length, right? There's two lengths. There's the length here and there's a length here, and this is the width here and width here. So in short, you can say that the perimeter, when you're adding them all up, you can either say length plus width plus width, or you can say um, 2 length plus 2 width, right? Or you can say 2 on the outside, length plus width. So the equation can be reduced to that. And if you substitute our this equation to this equation, so let's do the substitution. So P equals 2, and it'll be L plus, and our width here, we're going to replace that with 60 over L. Okay, so so basically the whole point of substitution is that we have essentially two variables. And instead we have P and then we have L. And you put that, if you put that on a graph, and you can go to desmos.com and you put that in a graph, you will end up with a graph that looks like that, and then you'll get some sort of curve like that. If you pop that in desmos.com, and let me take a look here. Yeah, and if you desmos.com will give us lowest point. Again, the only way to figure this out is if you go to this website here and drop it in, or if you have a graphing calculator or maybe Excel, a graphing program, it will show you this graph. But I'm writing it out here because I already know what it looks like, and I'm telling you that at the bottom of the graph is the least amount. Basically, this is P, and that here is L. When you're graphing it, here is the lowest perimeter possible because again, for an optimized shape, you want to have the lowest perimeter and the greatest amount of area. So here we're graphing perimeter over length, and the lowest perimeter is at the bottom end. And I believe if you drop that in a graph, it gives you a number of 7.76. So P equals 7.746. There, and that'll be in meters, I believe. Was it working in meters? It isn't. Yeah, meters. So we're working in meters here. I'm just gonna complete the M there, and that is about it. I think that's it for this lesson. If you round it up, it'll be well, I'm just gonna round it up to be 7.75 meters. There we go. So that's the entirety of the lesson. The homework is a little bit different than the lesson. I'm not gonna have you substitute one equation to each other because I think that's maybe a little too much for you guys. But you should know what an optimized shape looks like. You know, it has to look like either a square or a sphere. So just by looking at something, you can tell right away if it's an optimized shape or not. The closer it is to a sphere or a square, the more optimized it is. And that's the takeaway of this lesson. Okay, that's about it.